Can you
Just
tell
so we
me
can
if this
compare.
number, if this runs out to 0?
Alright, so we want to analyze this parallel circuit. Okay, same thing, start out with the chart. So we have 5 ohms, 3 ohms, 2 ohms, like so. Okay. I'm going to find the equivalent resistance of this circuit next. But remember, this is a parallel circuit, so you can't add them up and get 10. And 1/5 plus 1/3 plus 1/2 is not 1/10. Don't do that. Okay? You laugh. Trust me, I have seen it happen. I said 1/5 plus 1/3 plus 1/2 is not 1/10. Don't do that. So, 2 options. 1, common denominator. 2, you have a calculator. It has an x to the negative first button on it. Use it. Okay, one or the other. I mean, if the numbers are easy, like 5, 3, and 2, we can find a common denominator pretty quickly. Okay? If not, you have the calculator. I mean, if you have 17 and 53.8 and 24, don't waste your time finding a common denominator. Use your calculator's inverse key. Okay? So what would the common denominator be here?
30.
What is it?
30.
30. All right, so 1 over 5 is what over 30?
6.
6 over 30. Plus, all right, 1/3 would be 10 over 30, right? And 1/2 would be 15 over 30. Okay, so 6 and 10 is 16, and 15 is 31. So we have 31 over 30. Be very careful here. That is not the equivalent resistance. It's the reciprocal of the equivalent resistance. You have to flip the answer once you add the fractions. Look. So you add the reciprocals together, that gives you the reciprocal of the answer. So after you add, make sure you take the reciprocal of the answer. So the equivalent resistance equals 30 over 31, which is what as a decimal? 0.97, we'll say. Ohms. Okay. Now here's the thing. This entire circuit with 5, 3, and 2 has an equivalent resistance of 0.97 ohms. Now, people might be looking at that like, how is that possible? You got 5, 3, and 2, you got less than 1 here. The equivalent resistance of a parallel circuit will always be less than any individual resistor by itself. So if you look at them, the smallest one is 2. This number has to be smaller than even the smallest one. So that answer kind of makes sense to me. Okay? Alright, the next thing we did after we found the equivalent resistance was we found the total current. So I'm going to do that next. How much voltage is applied to this circuit? 9 volts. Yeah, the battery gives you 9 volts. What's the equivalent resistance of the circuit? 0.97 amps. So what do we get here for I? A little more than 9, right? 9.28 amps. Okay, a lot of times when I do this, I'll put I sub T to represent the total current. Now here's the thing, here's what you gotta watch out for. This 9.28 does not go in here. Because all the charge does not flow through this. All the charge doesn't flow through that, all the charge doesn't flow through that either. It splits up. The current splits. You have that, right? So this number actually doesn't show up in the chart anywhere here. Alright, we'll use it in the end to check and make sure we did it right. Right, but a lot of times they ask for this, so that's why I showed you how to do it anyway. It doesn't show up in the chart. What I do know, though, is they're all connected in parallel to the battery. So that tells me this gets 9 volts, this gets 9 volts, this gets 9 volts. The voltage is shared. Okay? Now, if I have V and I have R, can I get I? How do I do it? V over R, yeah. So rather than last time we multiplied across to get this, now we're dividing to get that. So 9/5 is what?
1.8.
1.8. 9 over 3 is 3 amps. 9 over 2 is
4.5.
4.5 amps. Now, if you did it right, the I column should add up to that, or close to it.
What's the one?
Alright? If you add those three together, what do we get? 9.3?
Yeah.
Close. Alright, it's just rounding. So if you did it right, your I column should add up to I total. Alright, and then how do you get power? V times I. So yeah, multiply, multiply, multiply. Let's do it. 9 times 1.8 is 16.2 watts. 27 watts. And what's this one?
40.5.
40.5, right? Alright. Look at how drastically different that is. If you took good notes, you probably have the chart from last time when we did series. Look at your power column for the series and look at your power column for the parallel. It's the same battery, it's the same resistors, and it's the same wires. The power is substantially different.
10 times more.
10 times, roughly?
Exactly.
Exactly 10.
For most of them. For 2 of them.
Okay? So,
Yeah, that's,
what's up?
it's not 10 times, it's like, they're like switched. Like the one for, in the first chart, the power from 2 is now like the power from 1.
Right. So, if you look, the other thing that's different now is which one uses the most power now? The one with the least resistance. When you had the series circuit, the one with the most resistance had the most power. It's different. Okay? But we definitely know for sure this uses way more power than the series did. How come? Well, because there's way less resistance. So if there's way less resistance and you're using the same voltage, you're going to get more current. And if you get more current, power equals IB,
Yeah, no.
you're going to definitely get
30
more
seconds.
power out of it as well. Okay? So if you have the option to hook things up in series or parallel and you're trying to maximize the power, you hook them up in parallel, definitely. All right, because parallel is going to get more power out of it than series will. Okay? You're not always looking to maximize the power, but it's good to know that. Questions? All right. Now, a couple of things. You saw how I